Okay, so today we're looking at polynomial equations for extension 2. So our learning intention is to have the knowledge in using polynomial understanding and complex numbers to solve polynomial equations. So here we need to remember what the remainder factor theorem is. We need to remember what the remainder factor theorem is. So if there's no remainder, then that means that that value is a factor, and then we should be able to find all other factors by dividing through. We need to be able to do long division of polynomials with complex numbers, find the complex roots of a polynomial, and factorize perfect cubes for this activity. So I've scanned these in as well, these notes. So first point is complex conjugate root theorem. So if a polynomial p of z equals 0, it has real coefficients, then if you have a root of a plus ib, where a and b are real numbers, then it's the other root will be its conjugate, a minus ib. So they come in pairs. If you have a given polynomial with real coefficients and a degree of n, so if the highest degree of that polynomial is odd, then p of 0 will have at least one root, and the complex roots will come in conjugate pairs. If the degree is even, then it will have an even number of real roots, or no real roots, and the complex roots will also come in conjugate pairs. So if p of 0 has a complex root alpha equals a plus ib, and conjugate alpha equals a minus ib, then it's written as x minus alpha, x times by x minus alpha, conjugate of alpha, which gives me x squared minus alpha plus conjugate alpha, x plus alpha times conjugate alpha. Okay, let's do some examples. Oh no, first thing, this used to be in the old Year 11 extension course, but they took it out. So just so that you know, I think I've shown it to you before. If you have a perfect cube, a cubed plus b cubed, well, if it's a plus, then it's a plus b multiplied by a squared minus ab plus b squared. And if it's negative, if it's subtraction, it's a minus b, a squared plus ab plus b squared. Okay, we'll be using that in one of the questions I've got here. All right, so let's look at this one. So we're going to factorize z to the 4 plus 10z squared plus 9. And so what we're going to do, I'm just trying to find my solutions. Okay, so if I do this, and let's say I use the quadratic formula to figure this one out. Okay, because it's to the power of 4, I can use a quadratic formula. So I'm going to have minus 10 plus or minus 10 squared minus 4ac over 2a. So just quickly, 10 squared minus 4 times what's 9, so 64. So I got negative 10 plus or minus 8 over 2. So I get negative 1 and negative 9. Okay, so these are my roots for this. So that means that that this would be z squared plus 1 z squared plus 9. Okay, because I'm adding these roots. So if I had negative 1, it turns out to be 0, and if I had negative 9, it would turn out to be 0 as well. Okay, so what I'm going to do now is basically try to factorize both these complex terms. Okay, so let's say z squared plus 9 equals 0, and z squared plus 1 equals 0. It means that z squared equals negative 1, and z squared equals negative 9. Well, if I take the square root of a negative number, I'm going to get I. Okay, so in this situation, I'm going to get plus or minus I. If I take the z squared of this, I'm going to basically get, well, that's going to be square root 3, negative square root 3, so it's going to get 3i plus or minus. Okay, so it means that this root here, that the factorization of the quadratic complex is actually z plus I, z minus I, so the conjugate pairs, with z plus 3i and z minus 3i. Okay, so therefore the roots are I, negative I, 3i, and negative 3i. Okay. And that's how to factorize this quadratic. Okay. So the idea, I'll just go through the steps. So looking at this, going through the steps, I got the quadratic formula to figure out what are the roots of this thing here. Once I've done that, I can then factorize this again by using the complex number theorem. Yeah. So this is the final factorization of that. Now note that this is highest degree of 4, so which 4 is an even polynomial. So it has an even number of real roots, which are or no real roots, and so the complex root comes in conjugate pairs. Okay, so that's how that one worked. All right, let's look at this one. So I've got z cubed minus 8. So this is 8 is a perfect cube. So I've actually got this a cubed minus b cubed. So really, if we factorize, knowing that, if we can factorize it going z minus 2, z squared, that's plus 2z, and plus 2 squared, which is 4. Okay, so that's using this rule. So z squared minus 2, yep, okay. So now what I want to do is really factorize this. Okay, there's no real factors for this whole thing, so there's no two numbers, or two. How's that? Yep, there's no two numbers. The multiply are going to give you 4, but add together give you 2. So for this part, let's complete the square. Alright, so we get z squared plus 2z plus 1. Because that will give me z plus 1 all squared. And that gives me negative 3. Okay, so if I take the square root of that, yeah, that's technically that. And now if I subtract 1 from each side, cool. So my roots are going to be z and conjugate z. So it'll be z minus 2, because these are the roots, so it's going to be z plus 1 plus I root 3, and z plus 1 minus I root 3. Okay, and that's that. So I really should put down, for one of the success criteria, is being able to complete the square. Okay. Now notice that that's an odd degree. So if it's an odd degree, it has at least one real root. That's there. And the complex roots become in conjugate pairs. Okay, so that's that. All right. Next example. All right. We want to find all the roots of Z4. I think there was square root signs on those two. Nope. Okay, that's the question. Yep. So there's a polynomial if one of the roots, or z equals I, is a root. Okay. So if z equals I is a root, yeah, it's a complex root, therefore z equals negative I is also a root. Okay. So what we would have is technically we're going to have z plus I, z minus I. Okay, that's going to be that's going to be a root, and it's going to be something else. Okay, so if I just combine that together, I'm going to get z squared minus I, but that cancels out, minus I squared, which that's going to be negative 1. So it's going to be times a negative, so it's going to end up being z squared plus 1, is that part there. All right. So z squared plus 1 divided into z4 minus 2z3 minus 2z squared minus 2z minus 3. All right. So z squared into z4 goes twice. There's no z3, but there is one z2. All right. Let's subtract those together. That cancels out. Negative 2z cubed minus nothing is that. And then minus 2z cubed minus z squared is minus 3z squared. Okay. So that goes into 2z times. So 2z cubed minus 2z. Okay, so I'm going to subtract that. That cancels out. That's going to still be minus 3z squared, minus 2, that disappears, so you get minus 3. So it's going to be minus 3 here, minus 3z squared, minus 3, so yeah, that cancels out. Cool. So what we're going to get is really, this is going to be z plus I, z minus I, times it by z squared minus 2z minus 3. Okay. Now, this can be factorized further as z minus 3 z plus 1. Alright, so therefore the roots are I and negative I, 3 and negative 1. So I remind you, if the polynomial is even, it has an even number of real roots, and it has conjugate pairs becoming complex numbers becoming conjugate pairs. Okay. All right. We're going to find the roots of P0 given that z equals ei to the pi on 4 is a root of this complex number. Okay, so if z equals ei pi on 4 is a root, then z equals e negative I pi on 4 is also a root. Now I'm going to use the multiplicity rule. I should have written this down, but basically it's the product of the roots will equal the constant. Yep. So here in this question, I know it's a degree of 3, so I'm going to have at least one real root and complex conjugate pairs. Well, I've already got the complex conjugate pairs. So let's say the roots were alpha, beta, gamma. If I multiply them together, that has to give me negative 1. Okay, so if I have that, and I have that, yep, then this equals just 1, right? So my other root has to be negative 1. So if I was to write it in factorized forms, I would have z minus ei pi on 4, z minus e negative I pi on 4, and because this is a root, I'd have z plus 1. Okay. The last one, we want to find the polynomial equation of a minimum degree with integer coefficients that has roots of z plus I and z minus 5. Okay. So to do this, we're going to look at obviously having z, let's start with that real root, so we're going to have minus 5, and then we're going to have z, let's do the first root, minus I plus 1 plus I. Now we need to have the conjugate for that as well, which is z minus 1 minus I. I should put these in their own brackets because they are the roots itself. Okay, so if I was to expand this part, I get z squared. So I could expand this one. So z squared, let's just do minus z 1 minus I minus z 1 plus I, and conjugate pairs cancel each other out. So that should be 1 plus 1 is 2. Okay. Z minus 5. Let's keep that z squared. Because they're all z, that is 1 minus I minus 1. That would be plus I. Minus I. Oh, sorry. Like that. Plus 2. Which cleans up to be z squared minus 2 plus 2. So z minus 5, z squared minus 2z plus 2. They want to keep going further, so let's expand. Z cubed minus 2z squared plus 2z minus 5z squared plus 10z minus 10 minus 7z squared plus 12z minus 10. Okay, and that's the polynomial. Okay, that's pretty much, so just a reminder, so you'll be successful if you can apply the remainder factor theorem, divide polynomials, find complex roots, factorize perfect squares, which is a bit new, and complete the square. Okay, good luck.